Hey everyone, I'm Erik Harutyunyan, working as computer vision researcher at Superannotate currently, and also master student at Technical University of Munich. And today I'll be presenting active learning for 3D mesh semantic segmentation. Okay, so let's start first about with talking about the data, and also we need to know why exactly during these last several years the interest in this 3D data is increasing. In the right-hand side, we see some examples of this 3D data. They are usually scans and of indoor scenes or outdoor scenes. So above, you see a scan of indoor scene, and these scenes usually are obtained with the RGBD cameras, and with these image and depth maps, they usually can make a reconstruction and obtain a 3D mesh model. And these mesh models are composed of vertices, like the point clouds in general. And also, we have the faces, or so to say, the triangles, which show which three vertices are connected with each other. So you can guess the amount of triangles is pretty high because you don't clearly see them, but you see a surface. And so a single point can be part of multiple triangles, as you can guess. But on the other side, the scene below is a LiDAR scene, or the outdoor scene obtained with a LiDAR sensor. And these scenes are usually obtained with a LiDAR sensor mounted on a car driving through some streets. And but these scenes differ from the indoor scenes with the fact that they only contain the point clouds and no surfaces are present there. Okay, and so yeah, these data you can imagine is much more precise compared to image data. For example, if used for autonomous driving scenarios or the autonomous agents operating in indoor scenarios. And they are usually preferred in these safety critical applications because you can imagine that for autonomous driving, every centimeter can matter. For example, if it should avoid some obstacle or even some collision. And yeah, so let's also talk about the task, so this 3D semantic segmentation. So it's pretty straightforward if you are familiar with usual semantic segmentation of images. So the goal is to label each point in this point cloud to one of the classes that we have in this data set. And usually we label the points in a scene using the position information like X, Y, Z coordinates of the point in the scene, also utilizing color information of the point, and also surface normal information. Yeah, so the task is, so we can say that this 3D semantic segmentation task is relatively recent, and the models are also relatively new. But the earliest methods tackling this problem are the point-based methods, and they usually utilize some shared multi-layer perceptron, and so each point is processed with this. And even I'll later present the architecture of the model, and you'll see that even in all layers of this network, the MLP is the same. And so you can imagine that these kind of networks are pretty small and also pretty fast. And that's why they are usually preferred when we are trying to perform some other task in addition to the downstream task of semantic segmentation, which is in our case the active learning. And yeah, so their advantage is, as I said, they're lightweight and fast, but they have also a disadvantage because you can imagine that because we are using some fully connected layers the shared MLP, it can't process the whole scene at once because we would have the tremendous amount of of neurons in the fully connected layer, because these kind of scenes usually contain some 500,000 points, for example, or even more. And that's why they process the scenes by dividing them in small chunks. You can imagine that we can, for example, put a 3D bounding box around the scene by finding the point with the minimal coordinates and also the maximal coordinates, and then chunk this bounding box into smaller rectangles and process, feed into the network the points that fall in these small chunks. Yeah, and examples of these kind of architectures are PointNet, PointNet++, and KPConv. And later solutions, I also forgot to mention that the one disadvantage in dividing the scene in small chunks, you can imagine that the network is not aware of the global context of the scene, because it only sees in one, we feed only a small chunk through the network, and it is not aware what other things are there on the other chunks in the scene. And then these sparse conv-based solutions came and replaced these point-based solutions. And they are using the ideas of sparse convolutions. And as you can guess, these point clouds, especially in the case of outdoor scenarios like LiDAR point clouds, are pretty sparse. And naturally, these sparse convolutions can be applied to them. And but they are not point-based solutions, which means that usually this 3D scene gets voxelized, and then they start these convolutions operate on the sparse voxels. But the greatest advantage that they have is that they process the whole scene at once, and we don't chunk it here, and so they naturally achieve higher accuracy, like mean intersection over union in case of the semantic segmentation task, because they are pretty aware of the global context. And the example of these networks are sparse ConvNet or Mix3D is the most recent one. Okay, so let's talk about the PointNet++ model, which I used in this active learning experiment, because, as I said, they are pretty lightweight and pretty easy to experiment with, because training also takes a small amount of time compared to the sparse conv-based networks. And yeah, so basically, as I said, they are lightweight, fast, and point-based approaches, and also easy to use. And you can see the architecture below. So they are composed, this PointNet++ is composed of set abstraction layers you can see on the left side, which in turn is composed of this sampling and grouping layer, followed by a PointNet layer. This PointNet layer is the shared MLP that I talked about on the previous slides. And everywhere where you see this PointNet layer, they use exactly the same MLP with the same weights, and that's why it is pretty lightweight. And you can imagine this network is as some kind of encoder-decoder architecture applied on point sets, because with sampling and grouping, we reduce the number of points that gets fed into the PointNet on the next layer. And also this, like the shared MLP doesn't change the XYZ coordinates of any points. It just changes the feature dimension. So as you can guess, for example, the points entering the this shared MLP in the beginning are of some dimensionality, for example 6, because we have the color information, RGB, and then followed also the point normal information. And it just transforms it to brings it to another dimensionality, and we proceed this way. But yeah, this encoder-decoder architecture, like as I said, is achieved through this sampling and grouping operation that is performed before feeding the PointNet. And on the right side, we have two options. So in our case, we will proceed with the upper part, which is corresponding for the segmentation. We can also, as you can imagine, perform a classification, because in 3D scenes we can also have this task. We can have a scan of a single object, and we only, for example, could need to classify it. But in our case, we need to segment, so we need to have a label for each point that was fed into the network. And so on the upper part is the segmentation part, which performs the upsampling with interpolation. And here we utilize a unit PointNet, which is something similar to one-on-one comps, and just is responsible for combining the higher dimensional feature maps that we had there. And yeah, we achieve final score, like point per point scores in the output, like it's the softmax scores that show the probability that a point belongs to that class. Okay, as I said, there are these three parts that we need to understand in the PointNet architecture, which is sampling. So we'll use this farthest point sampling, which is followed by grouping. I'll talk more specifically, explain each of them on the next slide. And then, yeah, it's followed by grouping, which is a simple ball query, and groups the points that fall in a ball around some chosen points. And then we feed it to the PointNet, which is the shared MLP, and which generates like the output features from some input features of this point clouds. Okay, so this farthest point sampling is some kind of it's something similar to K-means plus plus initialization, and we start with a random point from our point cloud, and then so imagine we need to choose some endpoints that are maximally cover our point cloud, which means that we start with a random point and then take the next point, which is farthest from the point we took before, which was taken randomly. And then the third one is taken the point that has the maximal distance from both of the points taken before, and so on. So why I said it's pretty similar to K-means initialization is it's the same thing mainly, but without any random sampling component which is present in the K-means initialization, K-means plus plus initialization. Okay, so as you can imagine, we did this sampling to get some centroid points because we needed to lower the number of points, as I said, in this set abstraction layer to be fed onto the following PointNet with shared MLP. So we did this and got the centroid points. And also we do this ball query, which means that we need to identify which points are in the neighborhood of the centroids we have chosen. So each point, you can imagine, gets assigned to a single centroid that's closest to it. And yeah, we have an alternative of k-nearest neighbor grouping, but this one is much easier to implement, which means also which is much faster, and also yeah, that's why we choose during our experiments, so that the training is significantly faster. And then finally, we need to generate features with a PointNet that uses the shared MLP. As I said, so this PointNet utilizes both. So it generates feature maps for both the big amount of points that we had, and also separately for only centroids, which is visualized in the picture on the right side. And later, it concatenates these features together, and this is the final feature map of a point that passes through a single set abstraction layer in this case. Okay, so we saw the architecture in depth, so to say, of the PointNet++. Now let's also talk about the active learning and what is it about generally. So usually we have, so when we start with an unlabeled pool of a data set, and we need to label. So ideally, if we have unlimited budget, we can label all of these unlabeled pools, but usually that's not the case, and maybe this unlabeled pool is too huge. And it would be ideal to select the most informative points, so to say, out of this unlabeled pool, and label only those points, and only those points will be used for training our ML or DL model. And this cycle is the whole life cycle, so to say, of an active learning methods, because it starts with an unlabeled pool. And in the beginning, you can imagine we can start with a random sample out of this unlabeled pool, and then ask a human annotator, for example, to label these points. And then we use all these labeled points as a training set and train a machine learning model on it. And later, we can use this machine learning model to process all the unlabeled points and see and get a score of information, so to say, for each of these unlabeled pools, each of the point in this unlabeled pool, and then see what are the most informative points here. One example of score of information can be the uncertainty that the model has on the points in the unlabeled pool. And so the points with highest uncertainty will be selected. Like if we need to select n points in every cycle, we'll select the n most the n points that where the model is the most uncertain, and ask the annotator to annotate these points, and then we add these points to the labeled pool that we have, so it gets bigger and bigger in each cycle, and we retrain the model on this bigger step, and so on. We perform this cycle, for example, as long as it takes until we reach our annotation budget, for example. Okay, let's talk about the specific approach. So as you can imagine, there can be so there are pretty much different ways to measure the informativeness of the points, and this Monte-Carlo Dropout is one way to achieve this. And what's the idea behind it? As you can see in the below, we have the same architecture of our PointNet, and this Monte-Carlo Dropout method is just says that when we have a trained model already, we can add a dropout layer, usually right before the final layer when we get the softmax softmax scores for each point. And we keep this dropout layer active during the inference. And for example, run inference several times on the same input point cloud. Say on the right side, I have the formula for this. Imagine you run for each input point cloud 20 times this network with the active dropout. And because the dropout is active and some weights are cut off randomly during each run, the output softmax probabilities can be pretty different. And on the points that the network is the most uncertain, these output probabilities will be very different, which will make the entropy score higher for these points that's computed above. And so we'll then select the point clouds that have the highest entropy score with this approach. Okay, and yeah, so let's also talk finally about the specific experiments that were performed. And for this experiment, we used the ScanNet dataset, which is an example of indoor scene dataset that I showed on the second slide in my presentation. And as you can imagine, we can perform experiments on different granularity levels. So to say, for example, scene level. So we can make this active learning algorithm run and then select whole scenes out of the pool. And this is the biggest granularity level, I would say. And then we can also select a segment from each scene. For example, we can have some over-segmentation of the scene, which doesn't show which doesn't have the class of a segment, but just segments it depending on the color or normal information. And then we can run the algorithm to just choose segments in each cycle. And then the lowest granularity level is choosing points. Like we can say that, for example, in each active learning cycle, we need to choose 100 points from each scene of our unlabeled pool. And we compare with each other three heuristics, the MC dropout heuristic, which is our active learning method. So we'll need to compare it to random choosing. So if it significantly outperforms the random choosing, this means that the active learning strategy works because we get significantly better results when training model on scenes or segments selected with this heuristic. And also the final one is the ground truth heuristic. So we can utilize the annotated ground truth of the scenes and, for example, select the scene. If we are working on a scene level granularity, we can select the scenes where our model performs poorly. So, for example, if we select 10 scenes in each step, we select the 10 ones that have the lowest mean intersection over union in these scenes with our trained model. And yeah, the metric that we'll compare in each cycle with each other is the point mean intersection over union. So let's start with the highest granularity level, which is the scene level. So we start with 30 randomly selected scenes. And in each active learning cycle, you can imagine the ground truth heuristic, as I said, selects the 30 scenes where our algorithm, where our model performs the worst. And then MC dropout, the active learning heuristic, selects scenes with highest mean uncertainty. So we can compute uncertainty for each point and then just compute the mean uncertainty for the scene. And then we choose scenes randomly out of the unlabeled pool. as you can see, starting from around 90 scenes, the active learning starts to outperform random selection by a significant margin. And so we can say that this active learning strategy can be considered working because, for example, in the small amount of scenes, the model maybe wasn't able to see some classes. For example, in that scenes, we could have some missing classes that both random and MC dropout failed to select. For example, no sofa were present in that indoor scene. And then the next experiment is slightly different from the previous one. We start with one random segment from each scene, each of the scene in the unlabeled pool, and then in each active learning cycle, this ground truth heuristic again selects one segment from each of the scene in the training pool by this heuristic, but with the highest number of mislabeled points in that segment. And then the MC dropout just selects the highest, takes the sum of uncertainties in these segments, and the segments with highest uncertainty get chosen here. And random, just selects the scenes randomly. As you can see, here we also have this kind of warm-up period where the performance of active learning and random are close to each other, and in this case it even some kind of, with a small margin down, performs it. But after we reach some number of segments, it starts to outperform the random curve and is getting closer and closer to the ground truth curve. And finally, we also performed the point level experiment. And in this case, we start with 100 random points from each scene. And then in each cycle, we select 100 random points with ground truth heuristic again. We just select 100 points from mislabeled points. And then with MC dropout, again with highest point uncertainties, 100 points, and then randomly. This graph, as you can see, again, after some number of points, we see the overperformance of MC dropout heuristic, but it's much more messy because the number of points that the model uses during training is pretty low, because we have 100 points from each scene, and you can imagine there are, for example, 1,200 scenes in total in the data set. So it doesn't see too much points during the training. And then finally, I want to talk also a little bit about future work. Currently, I would say a kind of a present work. And so the problem with this active learning methods, as you could guess from the presentation, is the speed in which they operate. So you can imagine if, for example, we want to implement them in an annotation tool. So we'll use a model to estimate the uncertainties of points. And this network, from each cycle, for example, if it selected some points and says, please annotate these points, recommends you to annotate that points. So the problem is that after you annotate them, it needs to be retrained on these new points that you annotated. And this training process is the biggest bottleneck here. And we try to speed up this training process, for example, so usually we retrain from scratch the model, but we want to try some few-shot learning or one-shot learning methodologies here to significantly speed up this training process that can be some kind of implemented in the annotation tool integrate it. And then you can imagine that besides this bottleneck, the second biggest bottleneck is the inference when we need to infer the uncertainties of the points using this PointNet with built-in Monte-Carlo Dropout. So we perform inference on the whole scene with this network 20 times nearly to get the uncertainty scores, and this can be pretty slow. And in this case, we need to also speed up the PointNet++ inference, or maybe even change to sparse convolutions and then speed up that network, that network's performance with some neural architecture search, or filter weight pruning, or some knowledge distillation approaches, which will hopefully make it real time and be easy to be integrated in annotation tools and used for in production, and not only like be some topic of research here. So that's all from my side here. Thank you for your attention.
Okay, now it's time for questions.
Thank you. Thank you a lot. And what's about the benchmarks?
Mm-hmm.
Have this problem treat the segmentation some benchmarks, some typical data sets, something like paper with code comparison?
Mm-hmm. Yeah, so I can share with you also the repository. It's an open source implementation. As I said, we perform the experiments in the on the ScanNet dataset, and we also benchmark the models there. So these evaluations are all done on this ScanNet datasets validation set, and we also currently, it's pretty recent, ran this active learning method until it reaches its plateau. So you can imagine we run as much cycles as needed, for example, to see what percent of the scenes need to be annotated to reach close to the close to the model trained on the whole data set. And we saw that nearly 40%, so we did this with the segment level approach. We showed that nearly 40% of segments from each scene need to be annotated to get a performance close to the original PointNet performance trained on the whole training set of the ScanNet. So it's something around 0.45 mean IOU. So yeah, it's a pretty early method, the PointNet++, and nowadays there are more like sophisticated methods achieving something around 0.7 mean IOU.
And maybe can I ask another question?
Yeah, sure.
About previous historical models, so to say.
Mm-hmm.
When we construct features from points,
Mm-hmm.
it was example that we construct features as centroids,
Mm-hmm.
clusters. But my input data for each point it's X, Y, Z, maybe RGB,
Mm-hmm.
nothing more. But can I expand centroids with some additional information? Not only X, Y, Z, and maybe mean RGB,
Mm-hmm.
but also deviation of RGB, maybe number of points in clusters.
Mm-hmm.
How I can construct?
For example, this kind of thing, an example of this kind of thing is this Felsenswalb's segmentation. I don't know whether you are familiar with it or not. So it's a pretty early method, around 2006, I think the paper was published. It constructs not only RGB or XYZ features, for example, for these points, but also computes point normals using the surface information given in these point clouds. And maybe I can refer you to this paper. And you can read it there.
Thank you. And last question.
Mm-hmm.
I understand how I can calculate IOU for two-dimensional image, but how I should calculate IOU point clouds, since I can place with not convex, something like that.
Mm-hmm.
I use something like Yerevan mesh.
Mm-hmm. Well, the IOU here is computed. For example, we know the ground truth class for each point in the point cloud, and we take all the points of this class. For example, we have,
Point to point.
mm-hmm, yeah, and then compare the class of the points.
Erik, thanks for the presentation. I have two questions. First of all, you said that the PointNet got the structure of the encoder and the decoder. So I'm curious that the first part of the encoder, it keeps the property of similarity between 3D objects. So is it good for you that is the representations?
Yeah, I
mesh?
see what is. I think it should keep, yeah, the similarity because otherwise, so it's also used for classification. So yeah,
that's why I'm
yeah,
asking.
that's my reasoning. So yeah, I think.
Okay, and one more question about the complexity of the training and the inference. So you said that every single layer here is MLPs, yeah, as far as I understood. So it's not that weighty, I think. So how much the parameters it has?
Well, then I don't remember the number of
Approximately,
parameters.
yeah.
Yeah, I would say it's something around 3-4 million parameters.
Oh, so this very small model. So have you tried the maybe mixed precision training and inference?
No, I haven't tried it.
So that wasn't on the slide, so I'm proposing to try.
Yeah, sure, thanks.
Okay, thank you a lot. It was unexpected to see the conversation about the three objects here. Thanks.
How do you calculate the point uncertainties? Is it just the confidence score of those points?
So as I said, a dropout layer is added to the trained network already, and it's kept active during the inference. And we run inference several times. And as you can imagine, because the dropout is active, we get different scores, different softmax scores for points. And then we can compute entropy value, for example, for each point, and use it as an uncertainty measure.
Thank you.